On this video, we will talk about exponential decay with emphasis on the population. So whether it's exponential decay or exponential growth, we still have the same equation. The difference only is in the rate. We'll see that in a moment. But first, if we read through the problem, I try to summarize all of that in this little table. T is the time, will be in years, and A will be the population. We're using that model. Now just put all the information we know on that table. First, 6 years ago, this is in the past, so we use -6. And the population was 1600. Today, at the moment, so we use time at 0. The population is 100. Oh, sorry, 1000. And the question asks, when will this happen? Which means whenever the population hit 100, that will be irreversible. So we don't know what will happen, but we know that the population will be 100 at that point. Right. What we're going to do is we're going to put this pair of information into the formula and try to find the missing information. So definitely we're not going to use this because we do not know the time yet. For those two, I will go with this one first. You'll see why in a minute. So first, if I use this information, meaning t equal to 0 and the population is 1000, so I put everything we know in that formula. I have A is equal to 1000. A naught we do not know. E to the power k t. We know t is equal to 0, so we put. Now the reason that we use this point first, because k times 0 is still 0, and e to 0 power is 1. And from there, we can solve for A naught. So we summarize, we have 1000. E naught, e to the 0 power. E to 0 power is 1. So this is equal to 1. So pretty much we will have 1000 is equal to A naught. And we can use that information and carry on to the next part, the next pair of data. Next, we will look at this set of data. We cannot do that yet because right now we know both the time and the population. That will be more useful to us. That will be the last thing we'll do. All right. So next, the time equal to -6, t equal to -6, and the population is 1600. We're going to substitute 1600 in for A and -6 in for T. By now, we also know that A naught is 1000. Right. So now we use this pair of data. 1600 for A. A naught is 1000. You can use that column too. and then e to the k, we don't know the rate, and time, we do know that is -6. Right. First, we multiply what we have on the exponent, and at the same time, we can also divide by 1,000 on both sides. We have 1.6. And that will be -6k. Next, we need to solve for k because we have everything else except for that. K is on the exponent. To solve for exponential equation, we need to take ln on both sides because those two, the bases are not the same. So I will take ln on both sides. With that, we take advantage of the properties of the log, where we can take the exponent and we move it outside, or we can pretty much cancel here. But let's just move this exponent outside as a coefficient. Now we have ln of e. Ln of e is equal to 1. This just equal to 1. So we have ln of 1.6 equal to -6. Times k. To solve for k, we take ln of 1.6 divided by -6, or we divide by -6 on both sides. So we have k we can leave it like that, or if we want the decimal approximation, will be about that, -0.0783. It makes sense now that the rate is negative because the population is decreasing, so the rate is supposed to be negative, and so we have that, which is good. So now if we go back to the formula for the exponential, in this case exponential decay, population and initial population we know is 1,000. That's what we know. The rate we now know is this. So pretty much now we know almost everything. The only thing we need to find now is the time. So find that. So now we go to this data. Now put in everything we know. The population now is 100. We put that in for A. Initial population is 1,000. We got that from the first part of the problem. The rate, we can either use the exact values or the approximation. We use the approximation there. Try to save space here. Right. And now we try to solve for t. We know everything else. The way we solve for t will be similar to what we did here, because the t is still on the exponent and we still solve the exponential equation. So the first step, we divide by 1,000. So we see exactly as we did before. And that gives us 0.1. Now we have exponential equation because the variable on the exponent. We do the same thing as we did before, taking ln on both sides. And the properties of the ln or the log, the natural log, or any log in general. We can move the exponent outside as a coefficient. And we still have ln of e. And ln of e is 1, so this is 1. So pretty much we only have this part. And we solve for t, so we divide this on both sides, run out of space, so just say t is equal to . And if we do that, we should get about 29.39 or so. 29.4. About that. But the question asks about the question, when will this happen? So we can say about 29.3 or about 29 years from now. And with that, we found the time that the population go to 100 with this model. I hope you find this video helpful. Thanks for watching.